All right, then here for number 15, we're asked, what's the proper description of a chemical equilibrium? And so at equilibrium, the rate of the forward reaction and the backward reaction are equal to one another. So it is not true that the reaction has stopped. It's not true that the concentration of products and reactants are equal, like we saw just in the previous example. There was a lot more product than reactant. It's not true that the rates of the forward and reverse reactions are zero. The reactions can be going very quickly, but the forward reaction and backward reaction both going very quickly, not going at zero. And then finally D is correct. The rates of the forward and reverse reactions are the same when chemical equilibrium is attained. Okay, a little bit more about that. When the reversible reaction given has reached a state of equilibrium, well, it's not true that no further action occurs. The reaction is still at the microscopic level. It's still proceeding to the left and to the right. I'm going to skip over B. I don't even want to think about that. I'll see if something's easier down here. For C, addition of a catalyst will cause formation of more NO. That's not true. Catalyst does not affect the equilibrium constant. But finally, D, at equilibrium, the concentration of each substance in the system is constant. Okay, once it's come into equilibrium, the amount of NO, N2, and O2, those will settle down. So say we've heated the system up, we've given it time to come to equilibrium, then once it's come to equilibrium, the concentrations will not be changing any longer. All right, this is going to require some work on my part. 17 here. So for 17, this is going to require the ice table. And so let me write my reaction first. X2 plus 2y is in equilibrium with 2Z. That's our reaction that we're talking about. And I says initial change in equilibrium. And we need to be talking about concentrations. And so it gives us that there's 12 moles of Z at the beginning, and that 12 moles of Z occupies the 2-liter reaction flask. And so 12 divided by 2, that means that the initial concentration of 2Z is 6 molar, and then it was the only thing that's put in, so the others, there's none of that in there. Now we need to think about what happens. So for this reaction to proceed to the left, I have to consume 2 molecules of Z. When I do that, I'll make 2 molecules of Y, and I'll make 1 molecule of X. So 0 plus X gives me X, 0 plus 2X gives me 2X, and this gives me a 6 molar minus 2X. Well, we would have a really long way to go here if we needed to solve the, if we needed to set this up, we'd need to solve a quadratic equation. That's a lot of work and a lot of places to make mistakes. And so I'm happy to report that, in fact, this gives us more information. It tells us at equilibrium, there's 6 moles of Y. That 6 moles of Y occupies the 2-liter flask. So at equilibrium, we have 3 molar concentration of Y. Okay, so 2X is equal to 3 molar. That would mean just X was equal to 1.5 molar. So it's half of it. And then, I'll write this one out. So 6 minus 2 times 1.5. 2 times 1.5 is 3. And so this one is also 3 molar. 3 molar, 3 molar, and 1.5 molar. So Kc is equal to concentration of Z squared over X2 times Y squared. My 3 molar for my Z value. I have 1.5 molar for my X, and I have, what is that, 3 molar for my a y, and that's squared. I could not even put some of this in the calculator, so cancel, cancel. I have 1 over 1.5, which is 1 over 3 over 2, which is 2 over 3, which is 0.667. Okay, now here with 19, we have a reaction. I'll write it out again, CO4, and that is a gas in equilibrium with solid nickel and 4 molecules of carbon monoxide gas. And we want to write that homogeneous rate constant expression. And so this doesn't contribute since it's a solid. And we've got CO raised to the 4th power and NiCO4 on the bottom. And so that would be answer A. All right, let's look at problem 20 here. So for this reaction, we're given initial concentrations, we're given initial rate data. And so this rate is equal to some rate constant K times the concentration of CH3Cl to some power, that's what we're trying to figure out what it is, and water to some other power. So CH3Cl to the x, H2O to the y. We're going to try to figure out the values of x and y. I'm going to take experiment 3 and 2, and I always like to take the faster rate and divide by the smaller rate because I get whole numbers and not some weird fraction. So rate 3 divided by rate 2 is equal to 5.81 divided by 1.45, which is equal to K, we don't know the value of K yet, times, we know these concentrations, 0.200, this is for methyl chloride to the X, and 0.400 to the Y, and K, it's still the same K constant because we're at the same temperature, 0.200x, 0.200y. Do a little bit more work here. This ends up being very close to 4. Go ahead and round it to 4. The k's fall out. The first term falls out completely because regardless of what the value of x is, it's the same on the top and bottom. Cancel, cancel. And so I'm left with 2 to the y is equal to 4. Therefore, y is equal to 2. All right, to get this other one, it's going to require a little bit more work on our part. Here I'm going to take rate, 2 and rate 1, and 1.45, 0.182, and K times okay, but I know the value for y now. Okay, the value for y now is 2. Okay, this ends up being 8. This left side here ends up being 8. And then the k's are going to fall out. And so I get 2 to the x times 2 2 to the 2. Okay, so therefore 2 to the x is equal to 2, and x is equal to 1. Okay, so this reaction, it's first order in methyl chloride, and it is second order in water. So that would be option B.